So we're continuing our derivation now of the limit as x approaches 0 from the right of sine x over x. We're actually caring about the two-sided limit, but this derivation, because I'm referring back to this picture that puts me in quadrant 1, I'm actually only deriving the one-sided limit from the right. I've made a note here, the two-sided limit is the same. I'm simply telling you that, okay? We're not going to go through the argument a second time in these videos. Just like with the product rule and the derivation there, I don't expect you to have this memorized. I don't want you to regurgitate it at any point, okay? But I do want you to study it. So I could ask you questions about it, and it's possible that I would modify things and ask you questions about the limit from the left, where the picture would be down here in quadrant 4 instead. You'll probably see some of that in the check-in questions that go with these videos. Okay, so you should study this, but don't feel like you'll be asked to do the whole thing. I would ask you about individual pieces. I think in the past, I've done something like drawn this picture and said, what's the area of the little triangle? And people had to figure out that the area of that little triangle was sine of x over 2. So that's the sort of thing that I would hold you responsible for. All right, now it's not at all obvious why this is going to help us with getting to sine x over x, because that's what I want to have in the middle if I'm trying to use Squeeze theorem. Now I see a sine x on top here, but that's the left side, that's not the middle. I see an x here, but it's on top. What a mess. Okay. Well, what I'm going to do is I'm first of all just going to get rid of these 2's. Okay. So if I multiply through by 2, I can do that. 2's a positive number, so it's not going to change my inequalities. So I can say sine of x is less than or equal to x is less than or equal to tangent of x. And I'm actually going to just write tangent of x. I'm going to use my quotient identity and write that as sine x over cosine x. Okay, now in the middle, I want to get this. So I don't want x on top. I want x on bottom. So I'm going to take the reciprocal of these things. Okay. Now as I do that, I have to be careful. Here it's very important that I know that all of these things are positive. If I've got an inequality and I want to take the reciprocal to get a new inequality, that's only legal if everything is the same sign. I could do it if everything is positive, I could do it if everything is negative, but I can't do it if I've got mixed signs. Let's just compare things. I know that negative 1 is less than 2. Okay. I also know that positive 1 is less than 2. Now, if I take the reciprocals of things, when I take the reciprocal here, the reciprocal of negative 1 is negative 1, and that is still less than 1/2, which is the reciprocal of 2. Here, because these were opposite signs, that inequality is preserved. Negative numbers are always going to be less than positive numbers. Okay? So if I take the reciprocal of a negative, that's going to be less than the reciprocal of a positive. Not particularly helpful for what we're doing here. 1 is less than 2. If I take the reciprocal of 1, I get 1. If I take the reciprocal of 2, I get 1/2. We've just reversed that relationship. If things have the same sign, when you take the reciprocal, you reverse the inequality that describes that relationship. So I can do that. All of these things are positive. I can take the reciprocal, but when I do, these inequalities are going to change to greater thans. Okay. So I'll have 1 over sine of x is greater than or equal to 1 over x is greater than or equal to cosine of x over sine of x. And again, this holds for this picture, where x is representing a small positive angle. Okay, this does not hold in general, doesn't hold for big angles, doesn't hold for negative angles necessarily. It holds if x is an angle, a small angle in quadrant 1. Okay. Could even be a bigger angle in quadrant 1. It could go up to pi over 2, but that's what we're talking about. Okay, now this is looking a little bit more promising. Now I've got this x in the denominator here. I want this middle piece to look like sine of x over x, but I can see that to get there I'd want to multiply through by sine x, and that would actually make this piece and this piece both simpler, because they both currently have a sine x in the denominator. So I'm going to do that. I'm going to multiply through by sine of x, which I know is positive because I'm working with the case that x is an angle in quadrant 1. Again, if I were working with the limit coming in from the left, I could make a similar argument, but my signs, my SIGNs, my plus or minus signs, would be different, so I'd have to modify the argument. So when I do this, this is going to preserve these new greater than inequalities. So I'm going to have 1 is greater than or equal to sine x over x is greater than or equal to cosine of x. Excellent. That's the setup I want for the squeeze theorem, that the function whose limit I want to take is trapped in between two other functions. I'm viewing that one as a constant function. It's just a horizontal line. Okay. So if I were to graph this, I can say here's 1, and then I know what cosine of x looks like. Cosine looks like this. And so we're saying sine of x over x always has to be drawn in the region in between those two functions. And it does look like as we get closer and closer to 0, coming in from the right, because that's the only place where this inequality is valid, or where I demonstrated that this inequality is valid, it looks like my function is getting squeezed between those two functions. So let's just confirm that. Okay, I'm going to take the limit as x goes to 0 from the right of 1. Don't want to take the two-sided limit even though I can, because this inequality, I'll even explicitly write this, I've been saying it often enough, this is if x is a small positive angle. So this inequality I know is true if we're to the right of 0, but close to it. Okay, this limit would be 1. Let's take the limit as x goes to 0 from the right of cosine of x. Cosine of x is a trig function. Trig functions are continuous on their domain. I evaluate by plugging in, and cosine of 0 is 1. Oh, these guys are the same. That's exactly what I wanted. So now I can say, by the squeeze theorem, the limit as x goes to 0 from the right of sine x over x is 1. And this argument can be easily modified to show that the limit from the left is also 1. So I'm just going to say fact, which could also be verified by looking at the other one-sided limit and then observing that they're the same. The two-sided limit as x approaches 0 of sine x over x is 1. Not obvious, but true. Now, some of you may have had calculus before, in which case you may have learned a much easier way of figuring out this limit, and it's called L'Hopital's rule. We will be studying L'Hopital's rule later this semester. It's great. The problem is, in order to use L'Hopital's rule, you need to know what the derivative of, for this function, you would need to know what the derivative of sine of x is. We don't know that yet. We need to know what this limit is in order to figure out what the derivative of sine of x is. So, at this point, even if we knew L'Hopital's rule, we couldn't use it for this because we don't yet know the derivative of sine. Okay. And in general, I will let you know, directions on exams are going to say, use only those techniques of calculus we have covered this semester. So, once we've covered L'Hopital's rule, you're allowed to use L'Hopital's rule unless I say do this without using L'Hopital's rule. Okay? But if you know L'Hopital's rule and we haven't covered it this semester, you're not allowed to use it unless you prove it. You can use the techniques that we've covered so far to prove L'Hopital's rule, maybe, and then you can use it, but it's much easier to just use what we've covered so far. Okay, so we were able to prove this, using the squeeze theorem.